project concerns an object which is called rosy gasket. This is an object, this is a subset of a triangle, which is defined by some subtractive algorithm inside. If you know Sierpinski triangle, which is you take a triangle and you get out the center triangle, and in 3 triangles that are left, you take out their center triangles, etc., you see some fractal object appearing, which is quite simple because it's very symmetric, so you can prove that it has measure 0, and you can prove also that count its Hausdorff dimension. Rosy gasket is the object that looks from far away quite the same as this one, Sierpinski triangle, but we don't know if what is its Hausdorff dimension. We know still that it's measure 0, and this object is nice because it appears in many dynamical systems as a space of parameters of interesting dynamical systems. And we try to generalize this definition in higher dimensions. So we can say that rosy gasket lives in a triangle. So now we're trying to find its brother, like the next object, but in a simplex, in tetrahedron. So that's what we are doing with Pascal and Paul. I like it a lot, this project, because it's between dynamics, combinatorics, and topology. So there are different mathematical directions that we can take at the same time. And it's working. We have found an object which seems to be corresponding to what we were searching for, and we see that it's working in some good sense. We have a good renormalization process on it, but we don't completely understand it. We have a proof, but we don't have a complete comprehension, so we will continue working on this. So I have been born in Moscow. My parents are mathematical professors of mathematics in the university. My grandfather on my mother's side was a researcher. He's actually quite known in France. He doesn't have the same name as I do. His name was Vladimir Beletsky, and he was working with celestial mechanics. And I even remember my supervisor here in France, he recommended me the book of Beletsky on essays of celestial motion, and that it's a very nice book. And I was telling my supervisor, you know, it's my grandfather, so I know this book. And he was quite surprised. So I think mathematics, I didn't really choose mathematics. Mathematics chose me in some sense. So in our family, it was like a basic choice by default to be a researcher in mathematics. I'm aware that it's not like this in many families in the world, but it was like this in mine. So I think I started doing mathematics just because it was around, and I continued doing it, and I do it today. So it was not a conscious choice, I think. Yes, about mathematics as a profession, I think I still am thinking about this. I don't have a permanent position. I did my PhD, and then I did a postdoc for 2 years. So I've been a researcher only for 6 years. And so I think each time I'm asking myself, like each day, let's say, or each year I'm asking myself, am I choosing mathematics? Is it my profession? Am I a mathematician? And I think for me it's easier to say just that I'm doing mathematics. I don't know if it lasts. For now I do it and I like it, and more and more mathematics becomes a part of me. And it's true that I do mathematics. This year I don't have a permanent position, so for me the plan for this year was to do some other projects which interest me, which are not related to mathematics. But what happened that I have proven a theorem this summer, which was kind of opening an interesting subject for me. So I couldn't really stop doing mathematics, so I continued doing mathematics. So yeah, I still don't know about professional choices. I think life is so long. So I can't say, you know, it's like I'm not married to mathematics till the last day which will separate us. I think it's, I try to stay flexible and see how it goes. But for now I like it, so I continue doing it. My first memories of mathematics, I think they were in school when I was very young, even like in the first classes. We had one teacher for all the subjects, so I really liked just working with numbers or geometric forms, and I also liked that the one teacher represented all the subjects, and mathematics included, and I really felt that there is knowledge and mathematics as a part of it, and not like some separate subject. And then when mathematics advanced, in the middle school, like when I was 12 or 13, I think I got interested in plane geometry problems. Since I'm Russian, in Russia we have this tradition of plane geometry in schools. I think it's a very good way to enter mathematics. For me, at least, it was the way, because you have very simple objects, which are lines, triangles, circles. And already with these very simple objects, there are many beautiful theorems, and I was trying to find proofs, so I could understand what the proof means at this moment, because it was just a logical, very clear construction, one by one, the things were appearing. And one of the plane geometry problems I remember was a question: if you have a piece of paper and you have an angle, but its vertex is not on the paper, you just see two lines going from somewhere, and the question was to draw a bisector of this angle. And I remember that I have found 2 points. I just took 2 points on 2 lines, I connected them, and I drew bisectors of 2 angles that I could see, and I found a point, and I knew that since bisectors intersect in one point, this is a point on a bisector I'm searching for. And I was stuck then. I was like, how can I draw a line? I know one point on the line, but I can't find a line. And I remember my teacher coming and saying, but you have found the idea, just use it one more time. So I drew another triangle and I drew a line. But for me, it was quite a powerful thing, because I have found an idea. I was very happy, but it was still not working. And my teacher, she helped me to see that sometimes it's sufficient to kind of just continue in the same direction, be more persistent with the idea. And this is one of the memories I remember and try to use in my research since then. My research is in the area of dynamical systems. It's an area, very exciting area. I think it's quite new, quite young in mathematics. I would say it's just 3 centuries old, and this is the domain that studies everything that moves, more or less. If you have a movement, you want to model it, this is a dynamical system. It started with planetary motion, but you also can have motion of gas in some space. You can have anything you can imagine, the growth of trees, the growth of tumors, the traffic jams, everything can be modeled. And dynamical systems theory asks the question, what will happen with your particular system on a long term? How it will evolve? Does it have some periodic motions? Will all become chaotic, etc.? So these are the questions people who do dynamical systems are interested in. I am working lately, like last couple of years, I've been concentrating myself on simple systems coming from integrability, so systems that have many closed orbits, less chaotic but more periodic, and trying to understand their combinatorics. So the questions are a little bit different that in hyperbolic dynamics. They're more combinatorial, studying symbolic dynamics and things like this. So, for example, people who work with billiards often like to work with interval exchange transformations. We also do it, but I do it in the situation when internal exchange transformations can change the orientation, and this systems has very, very different properties than that of classical interval exchange transformations. Yes, so also I can say that my research has been changing a lot for the 6 years. I started with hyperbolic dynamics and some differential equations, and then I moved to algebraic geometry, complex and algebraic geometry, and now I'm moving to combinatorics and dynamics. So it's very, I'm still exploring mathematics. I feel I'm just learning mathematics around my research area. I don't remember the first Eureka. I don't think I did have very many of them, maybe one or two. I think the last one was when I have proven what is called a tree conjecture for tiling billiards. This one I remember very well, this moment that I was understanding that the proof is coming to its end. And I think it's very strong emotion because I really wanted to prove it for a very long time. And I was asking myself why the thing is happening. So the problem is that you just have a triangle tiling by one triangle. With some symmetries, you just take a triangle and you reflect it with respect to its, the middle of all of its edges. In this way you have a tiling. And then you have a billiard, which is a little bit original. You go in a straight line inside a triangle, and then each time you cross the edge between two tiles, you change the direction of light in a way that refraction coefficient is equal to -1. It means that if you take two tiles and you fold it, the line folds on itself, the trajectory folds on itself. And I was studying these systems, and it happens that there are many, many periodic trajectories, and it happens that these periodic trajectories never contour the triangle. They always contour the tree inside your tiling. So this was called a tree conjecture, and I wanted to prove it. Actually, I discovered this conjecture here in Cirm. There was a conference, and Diana Davis was saying, telling the story about the system and showing this conjecture. So we have seen many, many beautiful slides with something happening, which was mysterious, and I didn't know why it happens. And I was kind of obsessed with this question for 2 years, and I was very happy to prove it. And I think it was like in 2 steps. First, I have found the tool to prove this conjecture, which was to study foliations corresponding to these billiards. And when I found this tool, I had an idea of a proof, and I was actually very happy, and I thought I was finished. And then, so it was kind of Eureka, but it was a wrong Eureka because I understood that actually the proof is not yet there. And then maybe in half a year, I found another tool which helped me finish the proof. But I was much more calm because I was like, okay, you remember, Olga, that 6 months before you were thinking you have a proof, but you don't. So just continue working and see if it goes. And it did actually. I could finish the proof, I could use all the elements, but it was much more calm, you know. I was just, I just do my work and this was done, but I was very happy when it was finished, and I'm very proud of this result. I do lots of popularization. I created a site about celestial mechanics, and now I have a cinema club in Lyon where we watch scientific movies and then discuss about them with people. I think the popularization activity is indeed very important because at least for me, I think it's sad to separate mathematics from a real world, from people who don't know or don't work with mathematics every day, but who have the sense of wonder and who want to know how the things work. So I know that people actually need it and are very happy to discuss science. So I think it's also our responsibility as scientists to share mathematics with people. And also for me personally, I think I have this need to share and to connect, for example, cinema and mathematics, or theater and mathematics, or just images and mathematics. I think it's just things I like, and I want them to have some general coherence. So for me, it's a win-win because I think it's important for society, and I also like doing it. And I also think that speaking to young people is very important because I know for myself that I was in this Russian school for mathematicians. So I have seen, in Russia we have this big tradition of specialized school when we have more mathematics. And I was seeing so many mathematicians just pass by every day. So for me it was very natural to become a mathematician just because I saw somebody who does this job. And I think some people maybe they would be great scientists, but they don't know that this possibility exists. And also just seeing people do some job and ask some question how it works. I think it can be very important for young people just to know how many choices they have. So I also try to, how I can to tell them about what is the job of the researcher and what mathematics for me is, and how it's very different from what someone can learn in school about mathematics sometimes. Even though for me, I think my school teachers were very important for me to be choosing this route. It's hard to explain why we are attracted to some area, mathematics or cinema or art in general. I think for me there is always this question like, what is the sense of what I'm doing? And I think many researchers in fundamental mathematics are asking ourselves this question. And of course, mathematics is useful and society needs mathematics to be useful. And I often hear people ask me, oh, but what does it, what for you need this theorem for? Since I'm dealing with very pure objects and pure mathematics. And for me, like, of course, I can explain that billiards are very important and ergodic theory is important to understand kinetic theory of gas or many other things in physics. So there is this very strong connection with reality. But at the same time, for me, it's not why I do mathematics. For me, it's more about kind of poetry of it, because it's just such a complex world, but it has so many connections in it, and it's just kind of fun to be inside it. And I want to transmit it, and I think art is a good form to transmit this feeling about mathematics, to speak about it in a less precise way, to just give the sense of wonder, because nobody asks you like, why does poetry exist or why it is useful? And mathematics is often, I feel, suffering from this usefulness pressure. But if you forget about usefulness for a couple hours and you just have fun proving things or not proving things, I think it's something that can be shared. For me, cinema and math are not so different like I feel when I do them. I feel it's cinema is about storytelling and structure and transformation. In mathematics also you tell yourself a story when you prove a theorem, and you have some structures and they have some relations. So the construction of a script in some sense is not very different from the construction of a theorem. At least I feel like this, but maybe I'm thinking about both of these things at the same time. I try to connect them because I want them to be connected. So I don't know if it's subjective or not, but that's how it is for me. I don't see much difference in the process of doing mathematics and in process of doing art. Although in mathematics you have more constraints. You can't do whatever you want. You have to respect the structure of the material. Even though in art also, if you speak with people who work with clay, for example, they say, this you can do because the clay will be too dry or will fall apart. So I think there are many similarities, and I mean, I'm not an only mathematician who is attracted by art. I think it's a very big percentage of mathematicians who have some other way to escape from mathematics also. I love Cirm. It's been maybe 10 times I have come already to Cirm in different conferences, and I mean, you have amazing Kalong nearby. You have everything you need here to work on mathematics. You don't need to think, where do I find food? Where do I find beautiful nature? Everything is around. The library, I think, is one of the best I've ever seen. So everything is here. Yeah, and I think like Cirm for me is as mathematics. Each time I go away from Cirm for some time, I want to come back. And yeah, it's a wonderful place.